There's a bell ringer for you to practice. We'll let you work on that before we get to the new stuff. You can unpause the video, or pause the video and check your answer in a minute. So how long is a wave? We're looking for a wavelength. We know frequency. We know those are related by the speed of light. If we're at 35 degrees, we can't use 343. We're 15 degrees Celsius change from that. Speed changes by 0.6 meters per second every 1 Celsius degree. Take your 15 times 0.6 and you get 9 meters per second. So instead of 343, you actually have to add a 9 to that to get 352 meters per second. We know the frequency is 512 hertz, and then we can solve for how long the wavelength is. So taking 352 divided by 512 gives us 0.688 meters for the wavelength. And let's look at 15.2. Start sound of music. Describe the origin of sound in general and in various instruments. Show an understanding of resonance applied to air columns, and then solve problems involving standing waves in resonant air columns. In order to have sound, something has to vibrate. So sound is produced by vibrating objects. When you talk, you put your hand on your vocal cords and you just kind of say something to the computer screen, you'll notice that your vocal cords are vibrating, and they vibrate back and forth. They cause the air particles to move, and that movement of air gets transmitted through the medium of air and eventually gets to your ear, and we can hear that. So something has to vibrate. For us, it's our vocal cords. For those of you that are in band and play brass instruments, it's your lips that vibrate. How about reed instruments? Well, I gave that one away. How about woodwinds? That would be the reed that's actually vibrating. Resonance is when an object vibrates with the same frequency. And you can increase the amplification of the vibration by simply applying small external forces at the same natural frequency of the object. Most pure substances have a natural frequency. And again, small little forces applied at the correct time, in line with the period, would cause the object to vibrate more and more and more. We've got a beaker here sitting on the counter, and if I hit that glass beaker, you can hear it vibrate in a specific pitch. Now if we applied that exact same pitch right next to that piece of glass, we could get that to vibrate a little more and more and more, and if you could even amplify it enough, it would vibrate enough to actually break. A closed tube resonator is exactly that. It's a tube that is only open at one end, and it will vibrate at interesting specific spots. This is what a closed tube resonator would look like. Notice it's closed on the left end, open on the right end. In order for a sound to vibrate through that tube, you need to have a node at the closed end and an antinode at the open end. So if we draw that, you'll end up seeing there's a standing wave with this type of a pattern. Well, L is the length of the tube. How much of a wavelength is that part? So if you think of a normal wavelength, for wave motion, you've got this. So the up and down pattern from here to here would be one wavelength. What we have in the tube is from the node to the highest point. So we really have this amount of a wave, which would be 1/4, or wavelength over 4. That would be the first place where something resonates in that tube. That would be the first pitch that would resonate if you had a wavelength equal to 4 times the length of the open tube. If we take that same open tube, closed tube, open at one end, again, anytime you've got a node at the closed end and an antinode at the open end, it will resonate. So this can happen at other places. You could have a compressed wave a little bit that looks like this. The parameters are still fit where we have a node at the left end and an antinode at the right end. But what does that wave pattern correspond to? Well, if you follow along, we went up, we went down, and we got to about here. So that would be 3/4 of a wavelength. And you could actually just keep going and going and going. The next one would look like something like that. And if you follow the wave pattern, you have, that'd be one wave, and now you have a fourth of the next. That length would correspond to 5/4 of a wavelength. Interesting enough, the difference between each of these resonant lengths is how much of a wavelength. The change in length of these tubes, in order to get a spot to resonate, whether you're going from 3/4 to 1/4 is a half a wavelength, or from 5/4 to 3/4, that's also 2/4, or 1/2 of a wavelength. So if you have a closed tube resonator and you get it to resonate at some point, and then you find another place where it resonates or gets louder, the difference between those two resonant spacings is 1/2 a wavelength. And that's for the closed tube resonator. The lowest place, or the first place where it will resonate, the fundamental, will be at 1/4 of a wavelength. Let's look at an open tube. This is just like a closed tube, but now it's open at both ends. So it kind of looks like this. And we'll do the same thing. We'll show what happens with 3 of these open tubes. Well, what kind of wave pattern do we need? What's the thing have to look like in the tube in order to resonate? Well, at the open end, it has to be an antinode. So the lowest place where we can have an antinode at both open ends would be something like that. And if we kind of go back to what a wavelength looks like, in this case, we've got from the highest right here down to the lowest right there, which is exactly 1/2 of a wavelength. So the length of this tube, it will resonate. Some noise will resonate or get louder if your wavelength over 2, or at a wavelength divided by 2 equaling the length of the tube. So if your wavelength is 2L in there, it's going to resonate. The next lowest space, where you start with an antinode and end with an antinode, would look like this. And that is actually one wave pattern. Starting low, going to the highest point, getting back to the lowest point, now you start repeating. So the length here is at exactly one wavelength. And the next lowest would look like this, and this corresponds to 1.5 or 3/2 wavelengths. So again, if I ask you, what is the spacings between resonances, or your resonant length, what's the change in length between places where it will get louder? Well, from the lowest one to the next lowest, the difference between wavelength and wavelength over 2 is exactly 1/2 a wavelength. If you go from here to here, 3/2 minus 1 is 1/2 a wavelength. So you get the exact same thing. Whether it's a closed tube or an open tube, the difference in the resonant spacings will always be 1/2 a wavelength. Now the difference between them is the first one will resonate in a closed tube at L equals wavelength over 4. In an open tube, the lowest one, the first one, will resonate at a wavelength, or L equals wavelength divided by 2. So closed was L equals wavelength over 4. The open is L equals wavelength divided by 2. Let's try a couple problems that correspond to this. I'm going to do a couple on page 363. So if you look at number 5 in your book, a 440 hertz tuning fork is held above a closed pipe. Find the spacings between resonances when the air temperature is 20 degrees. So I want to find the spacings between the resonances. What I want to find is delta L. Well, the spacing between resonances is exactly 1/2 of the wavelength. I don't know what the wavelength is, but I do know the frequency. And we know that frequency and wavelength are related by the speed of light, speed of sound. So if my temperature is 20 degrees, my velocity is 343, the wavelength I don't know, and the frequency they gave me was a 440 hertz tuning fork. So when you divide 343 by 440, you get a wavelength of 0.780 meters. If I then take this, plug it in here, 0.780 meters divided by 2 will tell me that every 0.390 meters, this particular closed tube should start to resonate. So if you can find a spot in that tube where it gets louder, and if you go another 39 centimeters longer, it should get louder again, and louder again, and louder again for that particular one. Every 39 centimeters or 0.39 meters. Let's try another one here. Number 6 says, and actually, let's do number 8. A bugle can be thought of as an open pipe. If a bugle were straightened out, it would be 2.65 meters long. So I have my open pipe. The length of this pipe is 2.65 meters. We're going to say the speed of sound is 343. Find the lowest frequency that is resonant. Well, for an open pipe, L equals wavelength over 2. That's the place where the lowest resonance occurs for an open tube resonator. And I'm trying to find the lowest frequency. Well, I know the length is 2.65 meters. That equals wavelength over 2. So if I double that, I can end up getting 5.30 meters, and that would be the wavelength. And then simply to find the frequency, all we have to do is convert that wavelength into frequency. My speed was 343 meters per second. My wavelength was 5.30 meters. So my frequency, when you divide 343, and I assume you're doing this at home, is 64.7 hertz. In that particular open tube, the lowest sound that will start to resonate will be at 64.7 hertz. To find the next two higher resonances in letter B, well, we know each of these resonances changes by a half. So the next one, L equals plain old wavelength. I know my wavelength, or I solve for my wavelength right here. Oh, just kidding. L, right here, is the length of the pipe. 2.65, that equals the wavelength. Plugging into this equation, 343 equals 2.65 times frequency. We can find the frequency very easily. It equals 129 hertz. And then I'll let you do the third one. Now for the third one, it's a half a wavelength higher. L equals 3 wavelength over 2. Again, we know the length is 2.65. Solve for the wavelength. And once you know the wavelength, you can get the frequency.